Hello everyone, let's go ahead and take a look at applications of geometric sequences. Now there's two primary applications that we'll be dealing with. One is called growth and decay, and the other is called compound interest. Now let's go ahead and start off with growth and decay. Here's our example. Let's say we have an initial bacterial population at time equals 0 is or was 1,000. Now the population decreases by 20%. 25% every hour. We want to go ahead and find a formula to represent the bacterial population and determine the population after 5 hours. Now, what's going to happen is that if you think about it, if we start off with 1,000, then we're going to actually decrease by 1/4 every time. So decrease by 1/4, decrease by 1/4, which means that we're multiplying 1/4 to each of the terms that we have, the sequence, to get the next subsequent value of the sequence. So therefore, we're dealing again with a geometric sequence. So therefore, our initial statement is going to be u sub n is equal to u sub 1 times about r to the n minus 1 power. Now that's when we're talking about general sequences. But we're talking about, in this particular situation, a population with regards to a particular time value. So let's go ahead and change this particular initial statement so that it takes into consideration p for population and t, which is time in hours. And so what I'll do is I'll just make that adjustment to say that the population sub t is going to be equal to p sub 0 times about r raised to the t power. Now I know that the initial population, or p sub 0, is going to be 1,000, and r, being that we know that it's going to decrease by 20%, 25% every hour, it's going to be 100%, which means that it's not changing at all, minus 25%, which is 75%. So this is the remaining population every time that we move incrementally in the sequence. So therefore, r is just going to be equal to 0.75 or 3/4. So now we can go ahead and substitute those particular r and p sub 0 values into my initial statement to find out that p sub t is just going to be equal to 1,000 times by 0.75 raised to the t power. Now, just to check and be sure that we've got the correct formula, I'm just going to go ahead and substitute 0 in for t to make sure that we come out with p sub 0 equals 1,000. And sure enough, 0.75 raised to the 0 power is just going to be 1. So 1 times by 1,000 is 1,000. And we can be sure that what we have is the correct expression for p sub t. So therefore, if I wanted to find out what the population is after 5 hours, well, t is just going to be equal to 5. So 1,000 times by 0.75 raised to the 5th power is going to be 237.304 ... And being that we're dealing with a number that is counted in terms of bacteria, then why don't we just go ahead and approximate p sub 5 to be 237 bacteria. So that's how we can go ahead and use geometric sequences and apply them to growth and decay situations. Now let's go ahead and take a look at this financial situation called compound interest. Now notice that what I'm going to do is I'm going to basically try to keep more or less the same values here. So notice that the initial bacterial population of t sub 0, t equals 0 was 1,000. I'm going to say that when you actually go ahead and you make a deposit, that initial deposit when t is equal to 0 is going to be $1,000. Now the interest rate is 25% per annual, which means per year. What is the principal after 5 years? So notice again, in this case the population decreased by 25% every hour. Now you're receiving interest, which means then that the rate is actually increasing, or is more than 100%. And so what we can see here is that r, instead of being a decrease in this case over here, because the population is decreasing, your principal is actually increasing by 25% every year, and so therefore r should be equal to 100 plus 25%, which is 1.25. Now again, notice that what I'm going to do is I'm going to try to change this original initial statement, which is true for general geometric sequences, and I'm going to adapt it to compound interest and say that the principal for any particular year t is going to be equal to p sub 0 times about r to the t. Now I know that p sub 0 again is going to be equal to 1,000, and r, as we described before, is going to be 1.25. So what I come out with then is that I get p sub t is going to be 1,000 times by 1.25 raised to the t power. Again, if I wanted to check, I could go ahead and substitute the value of 0 into t to make sure that we come out with 1,000 for p sub 0. which in this case I do. And I just want to go ahead now and find out what is my principal going to be after 5 years. So again, I just substitute the value of 5 into t and then come up with $3,051.76. Now, there's one particular situation that we need to be careful of when it comes to compound interest. Because what we're doing here is we're compounding interest once per year. Now, when it comes to financial situations, you don't necessarily always have to have that. And say, for example, in this particular situation, we're going to be compounding that monthly. Now, I'm going to change the value from 25 to 24, but leave the initial conditions the same. And in this time, I'm going to compound monthly. So that's the only change aside from the 25 and 24% that I'm changing. And watch how this affects the calculations. Now, what this means is notice that the initial statement is going to be exactly the same. My piece of 0 is going to be 1,000, which is exactly the same as well. But when I talk about the rate is different. Because what I'm going to do is I'm going to distribute that 24%, which is over 1 year, into 12 different parts. So what that means then is I'm actually taking 24% over 1 year, and I'm subdividing that 24% to 2% per month. So what that means then is that the rate now is going to be 100% plus 24% divided by 12, because I'm compounding it monthly, to come out with 102% or 1.02. Now, being that that's the case, notice that the rate here, where is it? The rate is right here, which is 1.02. Now notice that what I'm going to have to do is I'm also going to have to do this. I'm going to have to change this from t to 12 times t. Now the reason for that, of course, is because it's being compounded 12 times per year. So if I want to find out exactly how much money I'm going to have after 5 years, I've actually compounded it 60 times because it's once per month. So therefore, I come up with my formula for the compound interest to be p sub t is going to be equal to 1,000 times it by 1.02 times it by 12t. Now again, if I go ahead and substitute t equal 5, I'm going to have 1,000 times it by 1.02 times it by 60, and that's going to come up with $3,281.03. Okay, so let's kind of wrap up. Geometric sequences can be applied to both growth and decay problems as well as compound interest problems. It's going to be important that we take the initial statement for our general geometric sequences and apply them to our problem. And in addition to that, especially when we're dealing with compound interest, it's going to be very important for you to distinguish between situations where the compounding is done per annum or per year, as opposed to per month, or say, for example, biannually. So those little situations, those little changes in the vocabulary is going to change the way that you calculate your interest overall, so be very careful. Now again, we'll go ahead and take a look at some more examples the next time that we meet in class, so make sure to bring your questions to class. We'll see you then.